Hello, so I'm making this wee quick video today just to kind of show you where I would like you to go with some of the stuff that we're going to be moving on to. I apologise for my absence again. I know things are a wee bit higgledy-piggledy in the way that we're going about things, but I'm going to focus a wee bit today on trying to get us going with some other things. And the first one that's really important in the organic section is this idea of nucleophile and electrophiles. Now, I kind of started to mention this to a couple of years before, this idea of, phile being loving of something or being attracted to something, and that nucleo would come from nucleus and electro would come from electrons. So I'll not say too much about the points that I've made in here, okay? There's not a lot that just repeating them, it's simply what's in there. That nucleophiles are going to go looking for, the big thing that they're going to go looking for is, something that is going to be positive or partially positive. That's the big thing, okay, this thing here. And they do that because they themselves are electron rich, so they've got usually things like negative charges on them, or they've got lone pairs, or as it says in here, they have got polarized centers. Now, we've known since National 5 that the oxygen carries a delta negative charge. Since higher, we've understood why it carries a delta negative charge. So when we start looking at these polar bonds, a lot of times what we're going to find is in there's going to be something which is positive, slightly positively charged, and something which is slightly negative charged. So if we find molecules that have got an atom in there, a centre on them that's slightly negatively charged, in other words polarised, then they're usually going to be pretty good. They'll be able to act at least as nucleophiles. They're going to go look for something that's positive or slightly positive. Okay, so there's a few wee bits for you to read through in there. Again, it's going to be one of these things we're just going to try and get our head around it until I return. I don't know if this new chemistry teacher that's in is okay at teaching advanced higher. You're going to get someone teaching advanced higher. That would be ideal. If not, then we'll just need to plod on a little bit until we can come up with something better. Okay, electrophiles being the opposite of that, they are going to be electron deficient, so they're going to go look for electrons somewhere. They're able to accept electron pairs, and they are going to be attracted to and will attack species with a full or partial negative charge. In other words, the truth here is, in the simple fact at the end here, that nucleophiles and electrophiles are attracted to one another. It's quite a big thing in organic synthesis and organic reactions, this idea, a nucleophilic attack and electrophilic attack. And remember, there's not one without the other. If something's going to go and attack an electron rich, then it itself has to be electron poor and vice versa. So you're not going to get a nucleophile without an electrophile in there somewhere. It's just figuring out which one is which, and that'll come with a wee bit of practice in that. Again, any questions in it and why these things are that, you can get back to me. I'm going to jump on from this idea of nucleophiles and electrophiles to kind of introduce a key family, which is the halogenoalkanes, or the alkyl halides, or as we'll refer to them mostly, the haloalkanes. Now, we did look at primary, secondary and tertiary alkanols as part of the higher course. This is absolutely no different. Okay, it's the same rules on it. So if the carbon that the halogen is attached to is itself attached to at most one other carbon, then it's a primary haloalkane. If it's like a halomethane, then there would be no other carbon in there. But the same as we consider methanol to be a primary alkanol, the same rules go for there. So really there's no any difference between, other than the fact it's not an OH group we've got, but a halogen atom in there. There's no real difference between primary, secondary and tertiary when it comes to understanding them. It is crucial, and we'll see later on when we start looking at the mechanisms by which these things react. It is crucial to be able to recognise something as primary, secondary or tertiary. okay, because the mechanisms that are involved in it are slightly, at least can be slightly different, and indeed in the case of tertiary will always be slightly different than they are from primary. Secondary kind of hovers in the middle, but it usually goes one way. Okay, but that's for later on. Don't worry about that. Just try and recognise primary, secondary and tertiary and know that it will feature later on. Okay, again, it should be no surprise since National 5 to know that the carbon to fluorine or carbon to chlorine or carbon to bromine bond is going to be polar in there. That was a big part of Unit 1 higher. And so that's the same in here. So we're going to have the halogen atom carrying a slightly negative charge and the carbon atom carrying a slightly positive charge. Now, of course, for us, that's going to be a big thing in here now, because we're going to have this carbon atom in here as being electron deficient. And something which is electron rich, in other words, a nucleophile, is likely to go and attack that. Now, the big thing in being in this is that we are going to throw out and substitute. So what's going to happen is that the electrons that were part of this bond, which remember we're always favouring the halogen atom in any case, are going to come away, and we're going to end up with a halogen ion in there. Now, don't worry about that too much. What we're more concerned with as we go down this is what's going to come in here and throw this out, what's going to be substituted in there. There is things about this being called a leaving group, and obviously for something to leave, it's kind of got to say, well, there's a certain amount of stability associated with me. Am I okay being out there myself? I'm not going to leave this carbon bond, this covalent bond with the carbon here, unless I'm pretty much suited to exist as being myself. And that's what we'd call the thing being thrown out. We would call that a leaving group. Okay, so, and we'll come on to talk about that more and more. I appreciate these notes at the moment aren't up to where I'd like them to be, but just to give you an idea of this is what I'd like you to be thinking about as we go on. Okay, now we're doing reactions of haloalkanes. There's a few reactions of haloalkanes. Feel free again to make maybe wee flashcards about this. These are things that you've really got to try and get into your head. So the first one is that we have got an aqueous alkali to form alkanols. Okay, now notice that I'm putting in it's an aqueous alkali. Later on, we're going to look at what's called ethanolic alkalis. In other words, we're going to bring ethanol in there as like a solvent. And that things are different there than they are we're using water as a solvent. So it's a big thing. We don't want to be saying that this is an alkali that's going to form the alkanol in this. We want to say that it's under aqueous conditions. Okay, so typically, of course, since National 5, potassium hydroxide or sodium hydroxide we know are alkalis. Now what we're looking to get in here is that the OH minus ion that's part of that, if we jump back here, of course, is one of the nucleophiles that we look. It's got that negative charge on it, lone pairs of electrons. It's going to come in there and it's going to attack in here. Now again, we're not at the moment caring about the mechanism. The chlorine's going to come off here, become an ion, and what we're now going to get is an alkanol. Now that's useful for us to start off with these haloalkanes, because we know even from higher that, all right, primary alkanols, well, I can go down the route now of oxidizing them to alkanals and to oxidize alkanals to carboxylic acids. Okay, so it's a good synthesis route that we can go from with just starting with a haloalkane. Okay, right, so the second one that we would get in there would be alcoholic. Now notice in here that we're dealing with an alkanol, in this case methanol. It is possible to see ethanol in there as well as the alkanol. And alkoxide. Now this is going to be a new word to you. Okay, it was shown up here. That in here would be an alkoxide ion. That would actually be the methoxide ion. It comes from the corresponding alkanol, which has lost its hydrogen. Now, how it loses its hydrogen to become this methoxide or ethoxide, or okay, we'll leave it at ethoxide, I think, at the moment. Don't want to throw too much at you. How it becomes that, we'll look at later on. Okay, don't worry about that again, but just suffice it to say that effectively we can take an alkanol like ethanol and we can knock this thing off it, okay, to form that, and that would be the ethoxide ion. Okay, and again we are looking at it back to in there. These things which have a full negative charge are often very, very good nucleophiles. So in the example we're given in here, I'll just get rid of that methoxide ion. In the example we're given in here, then that's going to be the nucleophile that's going to go in and attack this slightly negatively charged, okay, nucleus. And it's going to go hunting in there, and off comes the bromine to become a bromide ion, and we're now going to form these wee thing called the ethers. Okay, now as you do that, and one of the things I'd like you to go back and just have a wee check, which I looked before, is, can you picture what the NMR spectrum of these things would start to look like again? Okay, could you picture what the NMR spectrum of something, let's just say that was CH3 in there, and that we were doing that with a haloethane molecule. Okay, and just always be thinking of NMR as we draw these things in here and look at them. Okay, other than that, and I know it's not easy to begin through this yourself, I really do appreciate it. I would maybe begin back and just trying to kind of plunder away again with Scholar. Hopefully by Thursday I'll put together some questions about these haloalkanes, nucleophiles and electrophiles, move on a wee bit more with some of the reactions of haloalkanes, and then start looking at the difference it makes in terms of primary, secondary or tertiary. Okay.